3, 2, 1. Let's get up on that catwalk. It's time to start modeling. Okay, so let's set some things up. Let's recall some things. Alright, so recall that dy dt. This represents the rate of change of a dependent variable y with respect to an independent variable t. The dependent variable y is a function of t. Right. Now, as we previously noted, pretty much any phenomenon involves something changing over time, whether you drop a pencil or you throw a ball, whatever you want to say. So that means that a first-order dE should be a reasonable representation of a physical process that involves a change. Okay. So today we're going to investigate three types of situations, three physical phenomena where something changes over time, and we can set up a dE to help us figure out how to model that behavior. Then we'll talk about the strengths and the weaknesses of these methods. All right, so the simplest model is a population model. This is known as Malthusian growth, and the idea is that a population changes based on how many members are present. So that's our operating assumption. So what we're assuming a population should do, right? In a simplest model. So what would it mean to change based on how many members are present, right? Another way of saying that is, well, the rate of change is proportional to the size, right? If you think about like the number of cells in like a bacteria culture or something, well, the rate at which it's changing should depend on how many are there, right? If there's a lot there, then there's a lot of possibility for multiplication of cells. If there's not a lot, well, maybe it starts off a little slow. Okay. So as a differential equation, then, specifically as an initial value problem, that means the rate of change proportional to its size means that there is some factor, a constant k, called the proportionality constant, so that the rate of change is proportional to the population itself. And P naught is what we'll call the initial population, and that should be, well, P of 0. Okay. So we have an IVP with two unknown parameters, k and P naught. Well, that doesn't stop me from solving it because, hey, the only thing that would solve this is a constant times e to the kt, and plugging in 0 just gives me the unknown constant, which would be the initial population, and so this IVP always has this solution. And there we go. The simplest model for modeling. For the simplest model in differential, simplest model of modeling, to model the models. Take a coffee break right there. I need some more energy. Got to get my brain juices going a little bit better there. Anyway, so yeah, pretty simple idea. Now that we converted something that we see in real life, populations changing over time, into a pretty simple IVP, and we've worked out a solution, let's unpack it. Okay, right, this is something you do in mathematical modeling, right? Once you've solved it, that doesn't mean you're done. Right now you have to go, well, does this answer make any sense? So the first thing to note is, if the population is 0, to begin with, it is always equal to 0. So if there's no initial population, there's no population ever. So this model preventing spontaneous growth from occurring. Okay, which, right, maybe that's true, but maybe sometimes you're in an area where animals weren't, but then they migrated over and they showed up. So this wouldn't be a good model for that, right? Like an invasive species, this would do a terrible job. This said there was never any species that were invading, so there never will be. Not necessarily the best. And speaking of not necessarily the best, when k is positive, if we look at the long-term behavior, well, I don't care what the initial population is, e to a gigantic positive number is going to be very gigantic. And note the notation I'm using here, this up arrow, is saying that p of t would increase to infinity. Right. If k was positive, this would blow off to infinity. Now, note the initial population, right, this wouldn't be a negative sign right here. This is a population, right, I could talk about like negative 14 birds or something. Right, that would be a positive number. part of the operating assumptions there as well. So it would blow off to infinity. So for long-term behavior, this model would be terrible, right? Because at some point, the population would exceed the number of known atoms in the universe. So, yeah, not a good one, but for long-term behavior. But in terms of short-term analysis, doesn't mean the model is total crap. It might do a very good job short-term, telling us, well, we should expect this kind of growth, maybe for like a couple of days before outside circumstances start interfering, right? Note that our model is taking place basically in physics heaven, where the only thing affecting the rate of change of the population is the population itself. Now, of course, in reality, that's not necessarily true, but for simple modeling purposes, maybe sometimes it does a good enough job. Now, one situation, if k is negative, then the population would decrease down to 0 as t goes to infinity. So this would do a great job for a population that we know would eventually vanish. So specifically, half-life. Yes, right. Well, we know something about certain radioactive isotopes, right? They decay as time goes on, and something we can measure is how long does it take for half of it to decay away. This is called half-life, and here you go. For example, the half-life of uranium-235 is 700 million years. Okay, so if we started with 10 grams of this stuff, we can ask, well, how long until we have 4? Okay. Now, before we get started, I do want to note, in the past, when I would set this problem up, I'd usually write it in a way so that I could then highlight the word half-life and the number 3. And then nobody would laugh. But then I would follow up explaining, like, Half-Life 3, it's a game that's never going to happen. And I would always follow up with, my favorite part of this joke is that I get to tell it for the rest of my life. But I guess, joke's on me, I suppose. Because I guess technically Half-Life Alyx is Half-Life 3? I don't know, who knows. Anyway. Alright, so let's actually solve this problem now. So let's let PFT be the amount of uranium-235 in grams. And now here is something that we haven't been doing at all, which is paying attention to units. And this is going to matter a lot in this class for these types of problems. We want to be very crystal clear when it comes to units. So we were told we've got we've got uranium in terms of grams. So we'll let P of T be the amount of it in grams, and T, to make our lives easy, will be measured in terms of millions of years. You could let T be years, but that would mean that, well, the half-life is 700 million, so you would have 700,000,000,000. If you want to do that, fine, but for us, we'll not deal with that. So we'll keep T in terms of millions of years, which means that I was told the following information. So first of all, we're told that the rate of change is proportional to its size. It's half-life, the amount of time it takes for half of it to vanish into the ether. It's not what it really does, but, Alright, it's changing at a rate proportional to its size. So we know that dp dt has to be some proportionality constant to p. Now, don't jump the gun and try to go like, oh, it's half-life, so I know what k needs to be. Don't do that. Don't. I know you want to do it. Don't do it. Trust me. Trust me. I'm going to do something that's going to blow your mind. Alright. Well, what else have I been told? Well, initially we were told that we have 100 grams of it. So at 0, the initial population is 100. Now, what else was I told? I was told what its half-life is. Its half-life is 700 million years, which means that at 700 million years, I should have 5 grams. Ah, there we go. There we go. All right. Excellent. So there we go. Beautiful. Okay. So what do we want to do? Well, we want to figure out when will I have 4. So I want to solve P of T equals 4. So obviously I need to know what P of T is equal to if I want to solve that. But before I even jump into that, we want to note something. It's got to be true that T is strictly greater than 700. right? This is decaying. So at 700 I have 5. Well, 4 is before 5, so as this decays away, we hit 5 first, so we should hit 4 later. So if I go ahead and I solve it and I get a time that is less than 700, I know something went wrong. And that's something else when it comes to modeling that you want to be doing. You want to be looking for things that would contradict modeling assumptions. Yes. Alright, so those are always good things to keep a lookout for. Anyway, so now that we know that, let's go ahead and actually solve this. So we know that P of t has to be 10 times e to the kt. That's just, right, we're dealing with proportional growth, Malthusian growth, as it is also known. And here you see I'm setting up the joke. So we know that that has to hold. Now we can solve for k because we were told that at 5 it is equal to, yes, when p is equal to 700. So plug that information and note that the 1/2 now has shown up. Yeah. And now note, k, the proportionality constant, was not just 1/2, or it was not just 2 or something like that. It's something much, 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 much different, right? And that's why I was like, hold the phone. Don't go all guns blazing into that. Note the negative log 2 is showing up because log of 1 over 2 is equal to negative log of 2, right? Log of 1 over x is always equal to negative log of x, right? Remember your log rules. Okay, but anyway, so we get k now, and it allows me to update the model, and I like to write it in this way, because now you can really see it. So something you can do at this point is e to the negative log 2 would be, of course, 1/2 raised to this power, but I like writing it out like this. There's like a general formula that you can put half-life into, but you don't need to go that crazy. You can leave it like this. But anyway, so updating the model, it looks like this. So, and again, I like this form because when you plug in 700, that turns into 1. E to the negative log 2 is 1/2, so there you go. It would 1/2 it, and for some reason that turned to a 100. What's going on there? I'm going to go ahead and fix that and look ahead to make sure nothing else is wrong, and nothing is. I just got a little too excited with the 0 key. Just anyway, okay. Oh, and by the magic of my brain, I was able to turn it into a 10. Alright, so we're not done, right? We have a question answer. When is it equal to 4 grams? Alright, well, set it equal to 4 and solve. Okay, so you divide it over the 10, you get the 2/5, you log both sides, solve it out. Now, before we reveal it here, we get this solution. You should maybe immediately start getting a little sweaty. And you're like, ooh, wait a minute, that doesn't look right. Right, that's a negative. I see a minus sign. That's not right. Negative time. That doesn't make any sense. But then, you don't notice it, but your brain does. Log of 2/5. 2/5 is less than 1. Log is increasing. Log of 1 is 0. So log of 2/5 better be a negative number. So this might at first glance look a little putrescent maybe. But don't worry, it's good, it's legit. This is a positive number. And by that token, log is increasing. So this ratio right here is bigger than 1. So this product right here, this number must be bigger than 700. So it does line up with our intuition on the modeling assumptions that the time it reaches 4 grams is something bigger than 700. Right? It needs to be, right? As we're decaying, we hit 5 first, then we'll hit 4. You don't hit 4 before you hit 5. You're decaying, you don't randomly just grow. It's not the way it works. Okay, so note, before I plug this into a calculator, or realistically, before I plug this in the Wolfram Alpha, right, I looked at my answer and I did a little analysis. I did a little evaluating, unpacked my answer, used my math knowledge, and go, this number does make sense. This number does work out. And it's in a nice closed form, which is the kind of things I prefer, right? We can, of course, plug it in and get some decimal. And yes, I deliberately went that far out so I could put that number right there. I do this problem a lot. This is the problem I always do, and I always do this. And I always go like, 666, funny. It's a funny number. And we get there. It's a funny number. It's a lot maybe more appropriate for class. There's some other funny numbers that I'll probably get in trouble if I joked about. But I don't know. Maybe I shouldn't be joking about 666. Yeah. Anyway. So incidentally, a little side note while you're reading this and working for the details. A student actually asked this question once about that, where I went out and found 666 in the solution here. They pulled up the digits of pi during class because, instead of like paying attention to the material, they're like, the professor did something dumb. Let me do something equally stupid. They pulled up the digits of pi and they found where 666 was in pi. And so, I had the class working on something, and I walked around and he showed me it, and he was like, "Hey, so there's 666 and pi," and I laughed at it. And then he followed up with like, "Wait, so any irrational number, right, the decimal never repeats and it goes on forever, does that mean 666 always shows up in every irrational number? Right, would it show up in the decimal expansion of square root of 2? Does it show up in the decimal expansion of e? All the other irrational numbers." And the student actually stumbled upon something that mathematicians legitimately study. That's something called a number being normal, right? Given any finite list of digits, will it always appear in the decimal expansion, right? An irrational number's decimal expansion, right, does not repeat and goes on forever. But that does not mean it hits every possible combination, right? There are irrational numbers that, even though they don't repeat and they go on forever, they still have very regular behavior. So, for example, if you do 1, 0, 1, 2 zeros, 1, 3 zeros, 1, 4 zeros, so on and so forth, that never repeats and that goes on forever, but it's very regular. So, which numbers actually have the property that you can find any finite string of digits appearing in their decimal expansion? That's actually an open problem. We don't even know if pi does that. So it's suspected it does when there's a lot of evidence for it. And it's actually, weirdly, it's a stupid thing to think about, but it is a very useful piece of information, right? Because if you can encode, anything as a finite string of numbers, right? In fact, you can do that in binary. So if we knew pi could do that, that means we can encode all possible information in pi. So, anyway. Yeah. I think I just spent like 5 minutes rambling about that. Whatever. You're watching this video at 12 speed anyway, so I can say whatever I want right now. All right. Okay. Well, let's heat things up here. All right. So now we talked about a very basic population model growth. Let's talk about another pretty basic model when it comes to temperature. So our good friend Newton, he came up with the following idea. He was like, well, let's say you want to measure the rate of change of an object. Well, the rate of change of an object should be proportional to the difference of the temperature of the object and the temperature of its surrounding medium, right? If you put something into an oven, if you put something into a fridge, right? It's in a fridge. It should be cooling down. And the rate at which it's cooling down should be, well, how hot was it to begin with? And, right, how cold is the fridge being kept at? Same idea with putting something in the oven. How cold was it to begin with? Right, usually why you want to get things at nice room temperature before you put it in the oven. Right, and how hot is the oven set at? Okay. As an initial value problem, this can be represented as follows, right? Proportional, right? Again, we mean the rate of change is a constant multiple of the difference of the temperature of the object T and the surrounding medium Tm. And T naught will be the initial temperature of the object. Okay, so there you go. Now, it's worth noting that this is, again, a nice separable DE, so we could work out the details and solve it, exactly how we did with Malthusian growth. But when it comes to the temperature rates of change like this, I like to just leave it like this and solve it on the fly every time, rather than having like a formula to plug in. The formula is a lot more complicated, so I'm not a fan of just having like the formula in your head ready to go. So I always do this out problem by problem basis. That's how I'm going to treat the next problem. So when it comes to Newton's heating and cooling, every differential equations textbook every single DiffyQ textbook. I have a lot of DiffyQ textbooks in my office. I've seen a lot of DiffyQ textbooks. Every single differential equations textbook, when it comes to heating and cooling, they always use the exact same example, because the people that wrote the book have a problem. Yep. A very classy problem. Okay, so suppose a lovely bottle of red wine, so like maybe a Bordeaux or something, which I think is, I don't know anything about wine, that was the first word that came into my head. Merlot, that's definitely a red wine, right? I don't know. You guys are totally of drinking age, right? I should be totally, this is what I should be talking about. This is straight from the book, by the way. This problem I took right out of the textbook, so this is legitimately in there. It's totally fine. So here at Iowa State, we have that like wine and spirits course, and that class is just like straight up like, yep, we're going to just talk about booze. The school I went to Clark's University. We had the same class, but it was sneaky. It wasn't just like an outright here's the booze class. It was a chemical engineering course, and it was called fermentation theory. Right, so like the description of the course made it seem like it was like a legit course about chemical engineering, but as I discovered, it's like, no, we just learned how to make alcohol. That was it. So every school's got the course in disguise, but the school I went to was a little bit more. They were a little more clever about it. But anyway, all right. So a bottle of red wine is brought from a wine cellar. The wine starts at a cool 10 degrees Celsius. It's left to breathe. You gotta let the tannins mellow. At a room temperature of 23 degrees Celsius. So if it takes 10 minutes for the wine to reach 15 degrees, when will it reach 18 degrees? All right. So let's unpack all the information we've been given. Okay. So we'll let T be the temperature of the wine in degrees Celsius, and little t be based in minutes. That is one of the more annoying things here, where we'll have a lowercase c and a capital T. When you type it out, it looks fine, but when you write it, that's another thing, by the way, why I don't have handwritten notes that I've been uploading here. Well, I actually have been uploading handwritten notes, and as you probably saw, my handwriting is, like, absolutely terrible, and as I've repeatedly mentioned, I probably drink too much coffee. Which I just finished my cup. And that's a problem. That's my problem right now. I don't have enough coffee in my I got too much blood in my caffeine system. That's my problem. Okay, so anyway, the information we're given, dt proportional to the difference of the temperature of our wine and the ambient temperature. So it's sitting in a room, and we're going to assume that the surrounding medium is kept at a consistent 23 degrees Celsius. Not necessarily true, but we'll just go ahead and assume that. Okay, so initially it starts off at 10 degrees Celsius, and in 10 minutes it reaches a temperature of 15 degrees Celsius. So there's all the information we've been given, and note that we want to figure out when will it hit 18 degrees Celsius. So we see here that it's increasing, 0 and 10. So what we want to happen then, well, before we go in solving it, we expect that the answer should be more than 10 minutes, so when we get there, we'll double check that. But let's get working. Okay, so let's first solve the DE. So as I noted, it is a separable differential equation, which means that it can be solved using the separable method, as per usual. So note, like I said, I didn't solve and give you a general form. I like to do these problems problem by problem case. It's worth noting that you can make this problem a little spicier if you wanted to. Instead of doing a constant room temperature of 23, we could do something like, oh, it's like a sine or something like that, right? The rate of change is oscillating, right? Temperature kind of oscillates. So that would make the problem a lot more complicated. So I'm not going to do that, but worth noting you could do it that way. All right, so let's now go ahead and solve the DE. Well, all right, integrates like that. And hey, there we go, we solved for t. All right, nothing too crazy there, but it is worth noting that we have two unknowns, a c and a k. Good thing I have two pieces of information to solve. All right, so let's plug that stuff in. So if you plug in the initial condition of t of 0 is equal to 10, we would get this, and solve for c. C is negative 13. Okay, now using the t of 10 equaling 15 allows us to solve for k. So plug all of that in. Note that I've updated my information. I know what c is equal to. It's negative 13. And we solve for k, and right, k is not exactly the most friendly thing in the world, but we got an answer. So, That's good. And so we can update the model, and there we go. So here, this is modeling the temperature of the wine as time goes on. Now, note some things about this right away. So you can check that the initial conditions that we were given, so the initial temperature and the temperature after 10 minutes, we can check that it actually spits out those numbers by plugging in things and checking. But now we can also note something. As t goes to infinity, this is log of a number less than 1, so that's negative. So this term would actually go to 0, which would then leave me with t is equal to 23. So that's saying that as time goes on, it should just reach the room temperature. Okay, so yeah, as a model, right before we even go ahead and solve the problem, as a model, we see here, yeah, that's doing a pretty good job. Seems like it's good. Right, and also note that right, E is going to be decreasing, and there's the minus sign, so it's actually increasing its way up to 23 degrees. Excellent. Okay, so if you want to figure out when we're equal to 18 degrees Celsius, well, right, just set it equal to 18 and solve, and we get that. All right, so again, we have this. What do we want to check? Well, we want to check a couple of things. Right. So log is a nice increasing function. Okay. And these inputs are negative numbers. So when I look at this fraction actually has to be bigger than 1. So the time when it reaches 18 is indeed bigger than the time when it hit 13. Right? It's 13? Yeah. It's 13? 15, sorry. I was like, I this 13 confused myself. I was like, yeah, it's 13, right? No, it's not. It's 13. Anyway, so before we even plug this into a calculator and get a decimal answer, we can look at this and go, well, yeah, I know this is going to be bigger than 10, so that makes sense. Right, so specifically, we can get boozy in about 19.68 minutes. I was hoping that I'd time this out a little bit better and that when I get here, it would be 19 minutes in the video. But as you can see, we're at 26 because I'm goofing off a little too much. I'm having a little too much fun. This stuff's fun. This is really cool stuff. These kind of really, these basic modeling principles. I took a mathematical modeling class. It was awesome. It was so cool. We did like stuff like this, and then you're like, well, let's mess with the model here. Yeah. The big project for that course was the professor. He never used his car, and so he wanted to figure out how long can he leave his car without turning it on before the battery dies. And he cooked up this model based off like how chemical batteries work, and we had to like sit down and like solve it, and then like we actually tested it, and that was a fun class. That was a good time. There was only like 4 of us in that class, but yeah. Anyway, all right, let's mix it up. I mean, we worked with we did some Half-Life and we got a little boozy. Let's mix it up now. All right. So the last type of mathematical modeling with first-order DEs that we're going to talk about is one that I'm a big fan of, and these are the mixture problems or mixture dynamics. Now, these problems are really fun because there's no general formula that works for every single one. So you have to, like, on the fly, really think about, how does this work and so these are, I like these a lot. So, you'd probably expect, maybe a problem to show up on a problem list or something. I don't know. Anyway, all right. So suppose that we've got a tank. We're performing some sort of experiment involving salt. The tank's got 200 liters of fluid in which 30 grams of salt have been dissolved. So it's, a nice brine. A brine with a salt concentration of 2 grams per liter is pumped in at a rate of 4 liters per minute. The solution is well mixed and pumped out at the same rate. Right, so well mixed here means that the salt is evenly distributed throughout the tank. So it's not like all the salt hanging out at the bottom or it's all on the top or anything like that. It's whatever turbine in there is moving it so that everything's nice and evenly distributed. Right. Without that assumption, this makes the problem a lot more difficult. But for us, we'll just go ahead and assume that. Okay, so yeah, it's a mixing problem. We got this going on. So we want to find an equation that models the amount of grams of salt in the tank as a function of time. That's pretty natural, right? So, a lot of mixture problems, mixture dynamic experiments, right? You're measuring, right, I'm mixing up fluids, and you want to measure, right, how much of a certain substance is going through the fluid, right? We always go with salt because brine is nice, but you have other sort of things dissolved in fluids. All right, so let's set it up. So word problems. So we want to start dissecting it, and I always like setting up variables first. That's something you should always do too. So we'll let A be the amount of salt in the tank in grams. We'll let lowercase t be the time in minutes. So A will be a function of t. Right, and I'm using the units I was given. So, right, grams of salt, time is in minutes. We're getting things pumped in minutes. And we're also told some information. We're told initially there are 30 grams of salt. Okay. So, note, A0 is not 200. Right, A is not measuring the amount of fluid in the tank. A is the amount of salt that is in the fluid in the tank. Okay, so we were told we started with 30, so be careful. It's a rookie mistake right there. Okay, so how are we going to set up a model? So the rate of change of the salt in the tank should be pretty simply modeled, right? It should be the difference of the salt coming in versus the salt going out. So the amount of salt coming in versus the amount of salt going out. So let's talk about the amount of salt going in. And before we do this, here's the key ingredient to these problems. Think about units. Salt is in grams, time is in minutes. So the units of DADT better be grams per minute. So that's going to help us. So coming in, we're told brine is pumped in at a rate of 4 liters per minute, and the concentration is 2 grams per liter. I want grams per minute, so the amount of salt coming in then is the product of these two. Ooh, computer almost fell. Caught it though. That would have been bad. Okay. Yeah. So, all right. Yeah. So the amount of salt coming in, the concentration of the salt times the flow rate. So there are 8 grams per minute coming in. Okay. Right. Note. I looked at the units, and I remember the units I need are grams per minute. I've got liter minute, gram minute, multiply them out, liters cancel. Right. Unit analysis. This is key when it comes to modeling. Right. Paying attention to your units. All right, now let's talk about going out. So the solution is pumped out at a rate of 4 liters per minute. Okay, so we have a flow rate, but what's the concentration, right? What are the grams per liter? Okay. We're assuming well mixed, so that means the concentration should simply be the current amount of salt divided by the current amount of liquid in the tank. Okay. Now, so what's the current amount of salt? The current amount of salt is A, right? A of T. Okay. What's the current amount of liquid? Yeah. Now here's where this problem gets exciting. So depending on the flow rates we're given, this could potentially be changing. But the flow rate coming in is 4, the flow rate going out is 4, so the amount of liquid in the tank never changes. And now, here's where it comes in. We were told there was 200 liters to begin with. So the going out part of it is going to be A divided by 200, right? Grams over liters. That's the concentration of the salt. So multiply it by the flow rate. And that gives me the amount of salt per minute in grams. Okay. And there we go. All right. So if somebody wants to get sassy on a problem, the amount of liquid coming in might be different than the amount of liquid coming out. And then you have to figure out, what's the current amount of liquid? In this case, the current amount of liquid is constant, right? Of course, in practice, it's not necessarily true, right? This is, again, a problem that's occurring in physics heaven, where, we're not assuming a billion things are affecting the system. Just the things we care about are actually what's going on with the problem. Okay, so now we figured out the rate of salt coming in and the rate of salt coming out. So then DADT is the difference of the two. So 8 minus 1/50th times A. The initial amount of salt in the tank is 30. And I am flailing my arms around, so I just flew through my headset. Yeah, I got, geez, all right. Good thing we're at the end of the video. I've just completely gone off the rails at this point. Okay, so that means that it's an IVP. It's a separate one. It looks pretty much just like the temperature problems that we looked at, so I won't go through the details, but the unique solution to this will indeed be A of T is equal to 400 minus 370 e to the negative t divided by 50. Okay. So you can verify that this works. Work in the details yourself. So good time to pause the video and work that out. Now, it is worth noting that as time goes on, e to a negative power, this decreases to 0, negating it, meaning that it would increase to 0. So the whole thing increases to 400 as time goes on. So long-term behavior, this settles to a constant amount of 400, right? So the transient term, this piece goes away, and the steady state part of it, it just ends up being a constant. So in the long term, eventually the amount of salt in the tank just becomes a nice constant 400. There we go. Beautiful. All right, so there we go. A nice smattering of examples of how we can use models. How we can use first-order differential equations to model some physical phenomena. Cool stuff. All right. Well, so that's it for today. Hope you liked it. I'll see you next time.